be able to dig into. The next one I wanted to go through was look at that counterfactual modeled example. So in the slide, so this is the, the Shire example. So in the slides here, and we'll work through this. And so these figures were all produced as part of this, this Jupyter notebook. So if people need to, they can access them that way, and can work through them kind of hand in hand. So again, we have two wells, a near well and a far well. We have monitoring data for the last 7 years at a quarterly rate. And there's a new activity that's happening. We want to see how frequently we need to monitor. Importing the data here, I'm just creating the time series, the model data, so that it's just available, and the observed data, obviously, this would normally be read in from your, from a CSV or from modeling output, what have you. We look at the monitoring data, right? We get these general values, and then we can estimate the standard deviation. In this case, where our model is simply the mean of that time series, and so our standard deviations come out at that 0.26 and 0.22 that I showed in the webinar. If we look at the model data, right, we have those near and far wells and those OK and trigger scenarios. That's all well and good. So now to actually calculate the detection power, it's relatively simple. You initialize the detection power calculator. Here we're using the Wilcoxon-Sang rank test so that we don't have to worry about our data being parametric or non-normal. We also set some values, so the minimum number of samples needed, etc. And we have the alternative question. Here we're saying we want to ask, is the alternative greater than the base? So in this case, our alternative is this trigger scenario, and our base is this blue scenario. Set up the sampling, the number of years that we want to sample, set up the sampling frequencies, and then it's really just plug and play. So here for the near well, we run a power calculation. We have an identifier value so that we can know what is what. We provide the error, in this case, the error in the base scenario. In this case, it's the near well. We have the option to set an error in the alternative scenario if you want to look at, scenario 1 has a lower standard deviation than scenario 2, for instance. If you set it to none, then it'll just assume the same as the base, and all that's described in the documentation for this function and for this class. We pass in the true concentration. So here so when you're passing these true concentrations in the base values, the non-automatic versions, they will be assumed that the sampling is at the right sampling frequency. So here, right, if it's monthly, then a quarter year step from 0 to 1, 2, or 3 years in order to get that true concentration. So that true concentration ends up at the right frequency. If you pass a different frequency in, it assesses it for the frequency that's there. So then you provide the base scenario and the alternative scenario. That's all great. There's also the opportunity to pass other quargs to this function, and those just get populated out into the output. So here I say the sampling years, I save the sampling years, and I save the sampling frequency. So those don't get used in the analysis, they just get passed straight through, but they'll show up in your data frame at the end so that you can query off of that. Same approach for the far detection power. And then it's just a matter of popping up the results. So here, sampling frequency, duration, and we can produce these plots based on the sample years and the power. And note that the power here is a percentage. Do people have questions in how that is run or how that is used? Would you like me to go over that in any more detail?